All right, this lecture is going to be about effect size. So when we do statistical significance testing, it determines whether or not there is an effect. We either reject the null hypothesis and determine that there is a difference between means, or we don't. So this is really a binary decision. Yes, we reject the null hypothesis, there is an effect, or no, there isn't. But it doesn't convey the size of the observed effect. So in the previous example that we've been working with, we concluded that our class raises LSAT scores, that there was a statistically significant effect, okay, that our class raised scores. But we didn't say anything about how much our class raises scores. So that's what effect size is going to be able to tell us. Effect size is a standardized measure of the magnitude of the difference between two populations. And by magnitude of the difference, this is often conceptualized as the lack of overlap between two populations. So in our example, we can think about a population of people that don't take our LSAT prep class and a population of people that do. And we can think about the distribution of those people in those two different populations and the extent to which those distributions overlap or don't in terms of the scores that people get on the LSAT. Our formula for calculating effect size is right here. And so the statistic that we calculate is referred to as Cohen's D. Okay, this D statistic is named after the person that came up with it, Jacob Cohen. So what we see in the formula is we've got mu1 and mu2 divided by sigma, which is the population standard deviation. So in our example, mu1 is the mean from the population that receives the treatment. So in our example, this is the LSAT class. And mu2 is the mean from the known population that doesn't receive the treatment. That is, people that don't take the class. And this is our basis for the comparison distribution. Okay, so recall that in the conventions that we've been using, the second population is the untreated population. Okay, so that's our comparison distribution. And then, of course, sigma is the population standard deviation. So in our example, we are going to use the mean that we calculated in the sample of people that took our LSAT as our estimate of the population mean, mu1. So we don't actually know the true mean. We're going to estimate it. So we're going to use our sample mean as a point estimate for what we think the true population mean is. Okay, and then we started with the information that the mean among people that take the LSAT but don't take our prep class, their mean is 150. So we did know the population mean for the comparison distribution. And then we also have to know the population standard deviation. In this case, it's 10. Okay, so to figure out effect size, all we're going to do is plug in the formula. And so in this case, we've got 153 minus 150 over 10, which gives us 3 over 10, which gives us 0.3. All right. So the interpretation here is that the effect of our class was to raise LSAT scores by 3/10 of a standard deviation. So the nice thing about this D statistic is it communicates the size of an effect in a metric which can apply to anything really, because we're talking about standard deviation units. So very similar to z-scores, very similar to the z-tests that we've been doing. We're talking about a metric of standard deviations, and that kind of gives a similar reference point, regardless of what we're talking about. LSAT scores, scores on an anxiety inventory, scores on a depression inventory. It doesn't matter what the original metric is, we're communicating an effect in a standardized metric, that is standard deviation units. Keep skipping over that. Okay. So here's our general formula for effect size. As mu1, we're going to use the mean of population 1, and this really comes, this will be a hypothesized mean for the population that is subjected to some experimental manipulation or some treatment. So this is a treated population. Mean number 2, mu2, is the mean of the comparison distribution. In other words, the distribution that is associated with the null hypothesis, the untreated distribution of people. And then sigma is the standard deviation of population 2. Now, critically, it's assumed to be the standard deviation of both populations. One assumption of doing the tests that we're doing that we haven't really covered so far is that the standard deviation of both populations, that is population 1 and population 2, are equal. So if you know the standard deviation for population 2, you also know the standard deviation for population 1. They're assumed to be equal. All right, so when we compute a D, Cohen also came up with different conventions to communicate whether there's a small, medium, or large effect. That is, whether the difference between the means of the two populations, it should be considered a small difference, a medium difference, or a large difference. And so a D of 0.2, that is anything that would, any type of a treatment or an intervention that would either increase or decrease a mean difference by 0.2 of a standard deviation would be considered a small effect. Any type of a treatment or an intervention that would increase or decrease the difference between two means by half of a standard deviation, 0.5 would be considered medium, and 0.8 would be considered large. And so this is a way that when researchers do the research, they're able to communicate whether, kind of like just how effective their intervention or their treatment is, that they'll communicate to their research audience using a D, just how effective their treatment was. So if they're coming up with like a new counseling technique to try and reduce anxiety, they could report that in a study that they did, they had some patients receive a standard treatment, other patients receive a new clinical treatment, and then that new treatment reduced anxiety by 0.8. And so that would be considered a large effect. Okay, that would be considered, if it's statistically significant and with a large effect, you'd say that that's a successful treatment. All right. So again, effect size is the amount, a couple things to know about effect size. The amount of overlap between those two populations is influenced by the mean difference between the two means and the population standard deviation. Okay, a standardized effect size adjusts the difference between the means for the standard deviation. So I'll go over some numbers that illustrates this. Okay. Again, the principle is that the amount of overlap is influenced by the mean difference as well as the population standard deviation. So with example 1, I present some numbers here where the mean difference increases, but it's the same standard deviation. So right here, what we see, this is just the effect size that we had previously calculated, where our LSAT class increased scores by 3 points. So we had a mean difference of 3, standard deviation of 10. That produces a D of 0.3. Well, if the population standard deviation, if we're talking about the same population standard deviation, but our LSAT prep class increased scores by 6 points, all else equal, you can see that that will produce a bigger D. Okay, so the amount of overlap is influenced by the mean difference. That's one factor. All right, and you can kind of go back to the previous pictures and imagine those two different distributions of those two curves, and they're just more separated here. They're further apart when a d is 0.6. It means there's less overlap. All right, but now with example 2, let's keep the same mean difference. So we have a 3-point mean difference. And now what we're going to do is we're just going to adjust the population standard deviation. Okay, so here's our first example where we got a d of 0.3. But let's take that same mean difference of 3 and imagine that we had started out with populations that had more variability. All right, you can think about those curves as being wider. There's more variability, there's more spread around the mean. Okay, so that d in this case would only be 0.15. And so you can just plug in the numbers. You've got 153 minus 150 is 3, divided by 20 will yield a d of 0.15. So there's less overlap with the same mean difference. With the same mean difference, there's more overlap because there's more variability. You got basically a wider distribution, a wider curve. And so kind of moving those means apart, there's more overlap than in the first case. However, in this example, in the third one, what happens when we have a population standard deviation of 5, you can see that the result is to have a d of 0.6. So there you kind of have to imagine in our brains that we've got more narrow curves, more narrow distributions. So moving those curves apart by 3 points results in less overlap, a bigger effect size. Okay, so just some numbers to illustrate that the effect size will be influenced by 2 factors. The first is the amount of mean difference between the means of the two populations, and the second is how much variability there is in the population. That is, how much spread there is. All else equal, in other words, for the same mean difference, if there's more variability, there'll be a smaller effect size and more overlap. If there's less variability, there will be a larger effect size and less overlap. Okay? All right. So effect size is important for a couple reasons. So one criticism of null hypothesis significance testing is that the term statistically significant can be misleading. In everyday language, significant means of great importance or noteworthy. But in statistical language, significant just means that the results are unlikely to occur if the null hypothesis is true. Strictly speaking, a statistically significant result means that the probability of getting our sample result, if we assume that the null is true, is less than 5%. Strictly speaking, that's what it means. That doesn't automatically mean that the results are practically important. As a way to illustrate this, let's just say you read the following statement on the Kaplan website. So Kaplan is a test prep company that makes the LSAT. They say our classes are guaranteed to work or your money back. How can we be so confident? Our research shows that our LSAT takers score statistically significantly higher than the average LSAT test taker. It sounds great, of course. That's really good for marketing their classes. But when we think about making purchasing decisions and being influenced by this type of marketing and paying our good money, we would want to have some more information. Like, we don't just want to know whether there's a statistically significant difference, but we want to know just how big is that difference. What could be the case is that there's a small but statistically significant difference between people that take their class and everybody else. And that small difference, while statistically significant, might not be practically important. That is, if they've done collected all types of data. They've got a huge sample size. They know that their results, you could say, are statistically reliable. That could be demonstrated even though their class only raises scores by 1 point. And that 1 point wouldn't necessarily be enough to um, uh, uh, be more than, say, a minimum score needed at a certain college or at a certain law school, beg pardon, that you're trying to get into. So the point is that in addition to statistical significance, the other piece of information that we need to pay attention to is the size of the effect. Okay, so moving on to the next topic, let's talk about statistical power. And I'll just say that this is a very difficult topic. Um, and it really helps to read the text as well when it comes to this topic, especially. So, yeah, I'll just say that is that this lecture is really meant to supplement what is in the textbook and not be a substitute for it. So please continue to read the textbook. All right. So generally speaking, power is the ability to achieve our goals, and the goal of a researcher conducting a study is to get a statistically significant result. Okay, assuming, of course, that the research hypothesis is true. So researchers that try to create a new drug that will reduce pain or cure cancer, or researchers that are trying to come up with a therapeutic intervention to reduce depression or reduce anxiety. If they think that they've got a successful drug or a successful therapy, and they do a study, they want to have the ability to get a statistically significant result, reject the null hypothesis, and therefore support the research hypothesis. That's the whole name of the game. So they want to have enough statistical power in order to reject the null hypothesis and find support for the research hypothesis. Otherwise, what is the point of doing the research? Statistical power is the probability that the study will produce a statistically significant result if the research hypothesis is true. Okay? And we can never really know whether the research hypothesis is true, but of course, all researchers, that's their assumption. That's their starting place. All right, so statistical power is a probability that the study will produce a statistically significant result if the research hypothesis is true, or if the alternative hypothesis is true. Those are synonyms. All right, so I'm going to show you some graphics here. These are very similar to what the text presents. They can be a little bit challenging to orient yourselves to, but I'll do my best to help with this. So this should be a graphic that we're familiar with at this point. And so what we've got here is a distribution of means that are based on the null hypothesis. So in other words, we can think about there's a population, there's a distribution, and this distribution of means is what is likely to occur based on a random sampling process. Okay? So if we take all possible random samples of a particular size, this is our pile of means. These are all the means that are likely to occur. This is the mean of means that is equal to the mean in the population, and then we can see that there's some spread, there's some standard error, okay? That this sampling distribution of the mean has a standard deviation, otherwise known as a standard error. Then what we do is we come up with a critical value. We've been using plus 1.64 or negative 1.64, or if we do a two-tailed test, we use positive 1.96 as well as negative 1.96. And our alpha level, by convention, 0.05, is that probability of making a type 1 error, that is, rejecting the null hypothesis when the null hypothesis is correct. But we will, alpha is also our level of statistical significance, so that if we get a sample result that falls in this critical region, we're going to reject the null hypothesis. Now, from a power perspective, That's what we want. We want to get a sample result that falls in this critical region, because if we do, we say, hey, that happens, assuming the null is true, a sample result that falls in this critical region happens less than 5% of the time if the null is true. Therefore, that's an unlikely result. I'm going to reject the null hypothesis, and I have support for my research hypothesis. So that's a good thing. We want to be falling in this zone if we believe that our research hypothesis is true. All right. So let's think about a distribution of means based on the alternative hypothesis. Now, if the null hypothesis is correct, there would be no difference between a distribution of means based on the null hypothesis and a distribution of means based on an alternative hypothesis. So for example, if our LSAT test prep class didn't work, you could think about a population of people that don't take our class, the population of people that do take our class, and if the null hypothesis is true, the populations are equal, which means that the distribution of means that result from a sampling process based on those populations are equal, right? So basically, on average, you see no difference between the people that take the class versus the people that don't, if the null hypothesis is true. Well, now remember, if statistical power is all about what happens if our alternative hypothesis is true. So let's imagine that the alternative hypothesis is actually true, our LSAT class works, and so you can kind of think about, because these folks took the class, that whole distribution is shifted over. It improves, right? So this is a distribution of means. You have to imagine that kind of at this upper level here, you've got all the people that took the class, they improved, and then if we do a random sampling process, this is the means that we're likely to get based on the class working, right? So let's just say that's true then. Our class works. Here's all the means that we could sample from the people that took our class if the class works. Interestingly, notice that everything to the right of the red line would be all the means that we could sample that would be above our critical level, okay? So if we sampled one of these means, we would reject the null hypothesis because it would land in the critical region in our null distribution, okay? So if we got one of these means, we're in good shape. It lands in the critical region. But notice that even if our class works, we still could get, on average, right? Like look at the difference here, right? Just because it works at a population level doesn't mean that when you sample from that population, you're always going to get means that are equal to the mean in the population. So it could be the case that even though our LSAT class works, we could take a random sample of people, calculate their mean, and we could have kind of a lower mean. And it would be so low that it wouldn't fall in the critical region on the distribution of means associated with the null hypothesis. Okay, so in that case, even though our class worked, it would be works at a population level, it would be possible to sample a mean that would be on the low end and that wouldn't provide sufficient evidence that it worked, because we would fail to land in the critical region and we wouldn't surpass our Z critical. Okay, and so that's beta. And so beta is our the probability of failing to reject the null hypothesis, even when the null hypothesis is false and the alternative is true. Okay, so beta is when we would fail to reject the null, even though we should have. Okay, beta is when we would fail to reject the null, even when our alternative hypothesis is true. Okay, so we don't want that. We don't want a beta error. What we want is power. Power is just the difference. If everything under the curve, these are all the possible means. So whatever the probability of beta is, 1 minus beta is our power. Okay, so if beta is 10%, power is 90%. If beta is 20%, power is 80%. All right. Okay, good. There we are. So power is what we want. So how do we get power? Well, here's a couple influences on power and ways to increase power. So one factor is the effect size. Generally speaking, the larger the effect, the more power. Okay. So what you can see here is what I'm illustrating is a smaller effect. So we've got an effect of our LSAT class. We've shifted over this distribution of means because we've shifted over people in the population. Their scores are better, but not by a lot. Okay. So in terms of all the means that we could sample from that treated population that does have improved test scores, this is the percentage of means that would be above our critical level, that would fall in this critical region, and beta would be the percentage that wouldn't. What happens if we have a larger effect? What we're doing is we're shifting over that distribution even more. So if there's a big effect on raising test scores, you can think about, moving from 150 to, let's just say this was our first example. Oh gosh, sorry. This was our first example, shifting over to say 153. Now we're going to shift over to 156. So larger effect. You can see the influence that we've got many more means here that would cross that threshold. So if we randomly sample from a population, we've got a higher percentage of means that we're likely to sample that would cross the threshold. Okay. So one principle, one way to increase power, which is to reject the null hypothesis when the null hypothesis is false and when the alternative hypothesis is true, is to have a large effect size. Is for your class to really work. So if your class really works, in other words, it has a large effect on increasing test scores, you do the study, you're going to be more likely to reject the null hypothesis because there's going to be a big difference between your mean and whatever mean is associated with the null hypothesis. So that's one, large effect size. All right. The second influence is sample size. So in general, the larger the sample size, the more power. And the primary influence, the way that works, is that a larger n will decrease the standard error of the mean. Recall that we calculate the standard error of the mean based on taking the variance in the population, dividing by n. That will give us the variance of the distribution of means, and then we take the square root to get the standard error. Okay. So the higher n, the smaller the standard error. So how does that affect our power? Well, so here's the first example. We've got, let's imagine we've got a smaller sample size. So you can look at the spread around the mean. Case 2, we've got a bigger sample size. So the effect is the same, that is, the difference between the means is the same, but the spread in the distribution of means is less. Okay? So case 1, case 2, case 1, case 2. Again, you'll notice that the mean difference is the same, but what's different is the spread of those distributions. So you can see because there's less variability, particularly really in both distributions, there's the means are more tightly clustered around each of the overall means or averages of the distribution of means. And so when that's the case, there's a higher probability of means from your distribution of means that are based on the research hypothesis to land in the critical region. All right. So that's a really tough concept. Hopefully the graphs are helpful in illustrating that. But if you can just remember the principle that the larger the n, the more power, you'll be in good shape. Okay? Think about it like this. It just really has to do with chance and probability. Like that would be the simplest way to understand it. Is that if you do a study with two people and you find a difference, you calculate the mean from those two people, and you find that that mean is different than something that you were expected, your confidence that that's likely due to something real versus randomness is going to be lower. But if we find that same difference and it's based on 200 people, we say to ourselves, oh, well, 200 people that got a mean that is different, that's much less likely to be an error than a mean that came from two people. Okay, so larger the n, more confidence that we don't have error that is associated with a sampling process from a population. Okay, the next influence is alpha level. So the principle here is that the larger the alpha, the smaller, in other words, the smaller and less extreme the critical value, and so the more power. All right, this one takes some unpacking. So in the first case, what we have here is a lower, more stringent alpha level. So our convention is to have an alpha level of 0.05. Here we've lowered the alpha level to 0.01. 0.01 is less than 0.05. We've lowered it. What that does, though, is it raises the critical value. So let's take a two-tailed test. Our critical values that are associated with a two-tailed test at 0.05 are plus and minus 1.96. If we lower our alpha level to 0.01 and we do a two-tailed test with an alpha at 0.01, our critical values increase to plus and minus 2.58. Okay? So we've made it more difficult for ourselves to find statistical significance because we've moved this critical value further out on the distribution. So there's fewer means that we could sample that are going to meet that threshold. Okay? But let's move our alpha back to our regular level, to 0.05. Okay? That critical region gets bigger, which means that there's more means that we could possibly sample from the distribution based on our research hypothesis that would cross that threshold. Okay? So here's a stringent alpha, a less stringent alpha. Stringent alpha, less stringent alpha. Again, you can see that there's fewer means that would cross the threshold, and there's more means that would cross the threshold. Okay? So in general, the larger the alpha, that is 0.05, the smaller the critical value, plus or minus 1.96, the more power. Okay? The smaller the alpha, 0.01, the larger the critical value, plus or minus 2.58, the less power. So here's a table that is presented in the book. These are practical ways of increasing power. One thing we talked about is if you're doing a study, one thing that you would want to do is have a big effect between your means. So if you're doing a LSAT prep class, you want to make sure that it was a really good class. If you're creating a drug, you want to make sure that it's a very powerful, efficacious drug. Okay, standard deviation is another big influence. So you want to have a less diverse population that is homogeneous. Okay, that's less good for other aspects that are associated with doing research, but purely from a statistical perspective, a more homogeneous, less diverse means less variability. It gives you a better chance of detecting an effect. Okay, using a larger sample size. This is probably the biggest influence. The higher the sample size, the less error, the more your ability to detect a true difference if it exists. Significance level, you can use a much more lenient level of statistical significance. Okay, so by convention we use 0.05, but you could be even more lenient. If you want more power, go even more lenient than the convention of 0.01. Okay, more stringent, going to an alpha of 0.01 makes things more hard on yourself. Okay. Using a one-tail versus a two-tail test. Okay, using a one-tail test, will give you a bigger critical region. Okay, so think about that. If you think that you're going to increase test scores, you want to put all of your 0.05 in the critical region. That makes it bigger than doing a two-tail test where you'd only have 0.025 in one tail and 0.025 in the other tail. So if you think that your intervention or your treatment or whatever you're doing has a direction to it, you should put all of your alpha in one of the tails. It makes the critical region bigger and makes it easier to reject the null if the null is false. Okay. And then type of hypothesis testing procedure. I'll not get into that, but there's certain statistical procedures that are more sensitive. But for the purposes of the exam, you should really just be able to know and recognize these 5 features. All right, just as a way to get some extra practice, especially because of how conceptually difficult this material is, I really suggest there's these how are you doing checks as you read the chapter. Try to do all of them. I think that they really help you answer the conceptual questions on the exam. And then if you need more practice problems, those are some set 1 problems that will give you some more practice. All right, that's it for this lecture.